Good morning, everyone. My name is Scott Muzenski. I'm here with my colleague, Naveen Saladi. We'll get two small miniature presentations today. They're kind of tied together, so lucky for you, two extra ones. The topic of our presentation today is ultra-high performance concrete bridge deck overlays as a corrosion mitigation strategy to ensure longer service life. So I'll start off talking about structural applications. Then I'll hand it over to Naveen, and he'll talk more on the material side. This is our disclaimer, as we are contractors for the Federal Highway Administration, so I'll skip over that real quick. So UHPC overlays have gained a lot of attention from bridge owners recently, especially when the alternative would be a complete deck replacement. So in some scenarios, a deck replacement would be necessary, but the fact that a UHPC overlay is possible, we're saving that from occurring. That's saving a lot of materials, it's saving a lot on construction costs, making it much more sustainable. We're all pretty much familiar with the properties of UHPC, but when we talk about UHPC overlays, the material itself is slightly different. One difference is that the rheology of the material in its fresh state is thixotropic in nature, meaning that it'll hold its shape until external vibration is applied to it. Another small difference is that the fiber volume in UHPC overlays is 3.25%, whereas a lot of conventional self-leveling, highly flowable UHPCs have fiber contents around 2%. So when we talk about sustainability, oftentimes we'll talk about LCAs and LCCAs. Where we will focus much of today's presentation is on the use phase. We know that UHPCs have high cement contents. They have, let's skip to that one. They have high cement contents, high fiber volumes. Those are all high initial costs from an environmental standpoint, from an actual money cost standpoint as well. But where we see a lot of advantages with UHPC is in its ability to have, optimized structural shapes, so we can use less material initially. Also, we have longer service lives, so that will provide us, obviously longer lifespan. We won't have to replace the material as soon. So that's where we need to focus our presentation today on. And when we talk about UHPC, we know initially the cost is going to be higher, but the long-term usage of the material is really where we need to focus. So, as I mentioned, we're going to kind of split this up into two different presentations, and we'll talk mainly about how we're going to use UHPC overlays to extend the lifespan of a bridge deck. But we need to make sure that this is going to happen. So, the first part, I'm going to talk a little bit about the structural performances of joints in UHPC overlays. We know that joints in UHPC are often going to be the weak link from both a structural standpoint and a durability standpoint. So if we can assure that it won't become a weak link, it becomes a material level property where we really see the benefits from a material standpoint. And that part two of that presentation, I'll hand it over to Naveen for that. So structural performance. So UHPC overlays are cast in phases. Often you're going to cast one lane, come back next day, day after, cast the second phase. There's going to be a cold joint between those two phases. That could be a weak link from a durability standpoint because chlorides, water, deleterious chemicals could penetrate that joint, get down into the concrete substrate, and cause even further issues in a deck that may already be prone to damage. From a structural standpoint, you could have cracks open up. You could have lack of stress transfer that is not going to provide the increased mechanical benefits that UHPC is known for. So this is where we're going to focus the structural testing portions. So what we did is we tested some UHPC overlay slabs in negative moment bending. We started off with a conventional concrete substrate. We cycled that for 1 million cycles to kind of represent a mature deck with some cracking in it already. Then we took those samples, we removed 1.5 inches via hydrodemolition, and then brought it back to our lab and cast UHPC overlays on that. So we'll have a full depth of 8 inches. And that UHPC overlay, the depth varied slightly due to the variances in the hydrodemolition process. But mainly what we were looking for is to test these overlays such that the UHPC portion itself will be in tension and it'll increase cracking, and then the joints will also be in tension too. So we're going to see how those joints, I guess, respond to the cyclic loading. And in a bridge deck, that joint is going to be longitudinal along the span of the bridge, but the deck itself, the forces or the moments may be perpendicular to that joint. So that's really where we're going to see some of these stresses come into play. So we looked at 3 different specimens. The first one was a reference specimen, no cold joint, no joints at all. The photograph on the bottom right, you can see what our test setup looked like. On the top right is a diagram of the test setup itself with some of the instrumentation we applied. We had LVDTs, strain gauges, obviously applying servo hydraulic forces onto the specimen as well. The next specimen we looked at was a simple vertical cold joint with a bonding agent. So essentially what we did is we cut half the specimen, or we took half the specimen and applied wood formwork, cast that first half of the UHPC. After 24 hours, we removed the formwork and we applied a bonding agent, a commercially available bonding agent, onto the vertical surface of that overlay, and then cast the second half of the UHPC. And then waited for it to cure and then continue testing. And then the last specimen we looked at was a stepped cold joint. So this is somewhat based on guidance that Swiss had put out in the past. So essentially what we did in this scenario is we dug a valley, an additional deeper valley along where we intend the joint to be. We had epoxy-coated double bars spanning that valley, and we created like a stepped formwork. That formwork also had an inform retarder on it, so that the intent when we demolded, it would expose that fiber reinforcement and then hopefully provide us a better bond when we do cast that second layer. So to get some of this, to get to testing of the material, obviously we've tested it under cyclic loading. One thing we did is we measured the stiffness during cycling. So the figure on the right kind of shows the flexural stiffness throughout cycling. What we did is we tested every 250,000 cycles monotonically from 0 load up to the maximum load. I forgot to explain this earlier, but we intended for all of them to last 2.5 million cycles. Initially, we would start with a lower force, which would be equivalent to, say, around 60% of the cracking stress of the UHPC. So regardless if there's a joint or not, we kept the loads the same. And then we gradually increase. Every 250,000 cycles, we would increase that load, and eventually we'd get to around 1.5 million cycles, where it would be equivalent to the cracking, the stresses in the overlay itself would be equivalent to the cracking stresses for UHPC. And then we cycled beyond that based off of a certain percentage of the localization strain. So for the step joint, it generally maintained throughout. For the reference specimen, with the exception of the first 500,000 cycles, it generally maintained up until that 1.5 million cycles, where that crack did form and then gradually declined. The stiffness declined at that point, and we had to stop around 2 million cycles, because you'll see on the next slide where a localization crack occurred. The bonding agent did not, the simple vertical joint with a bonding agent did not fare well. It continuously decreased flexural stiffness throughout. We also monitored the joint opening, so this is going to tell us, obviously the bigger the joint opening, the more chlorides can ingress, can get into the substrate, and potentially cause corrosion to any reinforcement below. Step joint, again, fared well. The reference specimen fared well until a localization crack occurred. So the figure on the top left here, you can see that localization crack at around 2 million cycles that opened up, and at that point we stopped testing. And then the bonding agent, the simple vertical joint, especially say at around 1.5 million cycles, it significantly opened up. You can see this crack, or joint opening, I guess would be the better term in this case, would be around 0.35 inches. Another thing that we noticed during testing is that the reference sample and the step joint sample generally maintained bond to the substrate. We did some NDE testing, non-destructive evaluation testing. We also did some sounding of the deck. The bond between the overlay and the substrate remained intact. However, the simple vertical joint with the bonding agent began to debond. We started noticing it earlier in cycling, but definitely towards the later ages as well. So to summarize some of our structural testing, the cyclic loading, when a UHPC overlay is in tension, and this is beyond the cracking limit of the UHPC, may result in reduced flexural stiffness, so we may want to be careful when designing the UHPC to hold loads beyond what they would with cracking. The cold joints created with a simple vertical joint with bonding agent at the interface were unable to sustain flexural stiffness, whereas the stepped cold joints were able to sustain through our initially intended 2.5 million cycles. So I'll hand it over to Naveen.
Thank you, Scott. All right, so I'm going to talk about UHPC bridge deck overlays as a corrosion mitigation strategy. So Scott talked about from a cold joints perspective, so I'm going to talk about when you have an active bridge deck undergoing corrosion and when you apply overlay, how's the corrosion performance going to look like. So it's a slight deviation from the joints, but still from a corrosion point of view. So the statement and objectives of this study, as we know, corrosion has become one of the leading contributors to bridge deck deterioration, leading to reduced deck capacity. So we have a lot of effective corrosion mitigation strategies, and our focus for this presentation are bridge deck overlays and corrosion mitigation chemicals. So as a part of that, we evaluated the performance of UHPC overlays by itself or in conjunction with different corrosion mitigation strategies. Sorry, I don't know why. So as a part of this study, we used A4 concrete, which is structural design mix, conforming to Virginia DOT requirements as the substrate concrete. And then we used steel reinforcement, grade 60 US number 4 steel as reinforcement in the substrate concrete. And we have two different overlays. One is a commercially available UHPC, and which is 1.5 inches thick, and one is a LMC overlay, which was done for comparison, and it was 2 inches thick. And the corrosion mitigation chemicals we used as a part of the study included a soy-based sealer, which is going to be identified as S1 through the rest of the presentation. And then we have amino alcohol-based corrosion inhibitor, which is going to be ECI1. And then two hybrid silane-based sealers and corrosion inhibitors, which are going to be identified as SC1 and SC2. So the specimen preparation and test matrix, the figure on the right you see, that's a summary of what we did. It's a lot of information, so because of the time constraints, I'm not going to go over a lot of that, but we do have a published document, FHWHRT 22087, where you can find the information regarding the specimen preparation. But I just wanted to point out just a quick summary of the specimen preparation. We have 4 different slabs. The slabs 1 and 2 have multiple test regions. Slabs 3 and 4 have a singular test region. And we did like the 8 different cases. So case 1 is a no overlay case. And then case 2 is a LMC overlay. Case 3 is UHPC overlay. Case 4 to 7 consists of UHPC overlays with the corrosion mitigation chemicals, and case 8 is UHPC overlays with clean rebars, where we excavated the substrate concrete underneath the top reinforcement, cleaned the corrosion products off of the top reinforcement, and then placed the UHPC overlay. So thickness of that particular case of overlay is approximately 4 inches. And then for the evaluating corrosion performance, we did 2 tests, corrosion potential and a cyclic polarization test, and then we evaluated bond performance between the overlays and the substrates using a direct tension bond testing. So here are the results for the corrosion potential. So the figure on the right, we measured corrosion potential over a period of 110 weeks. And as you can see, sorry, I forgot to mention this, but when we were preparing the substrate concrete prior to placing the overlays, we subjected the substrate concrete and the reinforcement through a multi-step chloride bonding so that it gets to a representative corrosion activity. So as you can see in the figure, we have the prior to placement bar, which is in the intermediate corrosion activity zone. So the procedure we employed prior to placing the overlays got all the reinforcement in all the cases to a slightly increased corrosion activity. And then we looked at application of overlays and different corrosion mitigation strategies, how the corrosion potential changed over time. So based on the C876 recommendations, the plot was divided into 3 zones: a lower probability of corrosion, intermediate, and a high probability of corrosion. So a general comparison, we have application of LMC and UHPC overlays reduced corrosion potential over time compared to the no overlay case, and inclusion of corrosion mitigation chemicals along with the UHPC overlays further reduced the corrosion potential. And case 8, which is the UHPC with clean rebar, gave us even more decrease in the corrosion potential. And then we looked at the cyclic polarization, which gives us information about the corrosion rates over time. The vertical line you see on the plot, it's a measurement that we took on the no overlay case, so it stayed consistent throughout the testing period. So we took a measurement prior to placing the overlay, and then 2 measurements after placing the overlay, and it was pretty much stable. Then we saw similar trends as we saw in cyclic polarization with all the other cases as to like how the corrosion rates change. So application of overlays reduced the corrosion potential, and then use of corrosion mitigation chemicals again further decreased the corrosion rate. And then case 8 gave even more decrease in the corrosion rate. So we got good information from the corrosion performance testing. So we then did bond performance to look at how the application of these different measures affected the bond from an early age perspective and a later age perspective. So the shaded regions that you see in the figure are the measurements that we took at the early age. So we saw no effect on bond in the early ages, but when we subjected the specimens through the testing period, towards the end of the testing period, when we tested the bond, we saw the cases which have the corrosion mitigation chemicals have a negative effect on the bond, and they had interface failure compared to all the other cases which had substrate failure, which is indicative of good bond. So to conclude, we used a commercially available UHPC material in combination with different chemicals, and we used the LMC overlay as a comparison. And then we saw that the use of overlays by themselves or in conjunction with CMCs reduce corrosion propensity, and LMC and UHPC overlays reduce corrosion rates by 20 and 50% respectively compared to the no overlay. And despite the reduced overlay thickness, the lower corrosion rates observed in the UHPCs could potentially be due to the lower permeability of the material compared to the LMC. And use of CMCs in combination with UHPC reduced the corrosion rates further, however affected the bond in a negative manner. These are some of the references we used throughout this presentation, and we'll take questions.